All right, let's hop to it. 2002, AB number 2. This is a rate in accumulation problem. Pretty straightforward. This is going to hit on the ideas of the integral of a rate function is total accumulation. And it looks like we've got another case of people going into, I don't know, is it an amusement park? Yep. The rate at which people enter an amusement park on a given day is modeled by E of t. The rate at which people leave the same park is L of t. And both E of t and L of t are measured in people per hour, and time is measured in hours after midnight. This is valid from 9 a.m. until 11 p.m. So time 9, time 23. The hours where the park is open. At time 9, there are no people in the park. So the park opens, one would think, at 9 a.m. Part A says, how many people have entered the park by 5 p.m.? So we're looking for the total accumulation of entrance into the park. The total accumulation of entrance into the park. So if we take from 9 when the park opens until 5 p.m., which is time 17, of our E of t function, we would be integrating a rate which would give us total accumulation. This, of course, is a calculator active question, so we'll want to grab our calculators to save us the trouble of trying to integrate this by hand. Grab your calculators. Okay, so clear out your home screen. Math 9 pulls up the integral command. We're going from 9 to 17, and then it looks like I'm starting to lose some pixels. No, I just typed that wrong. 9 to 17. There we go. 9 to 17, we want to type E of t. And some people's calculators, if you press alpha y equals, it pulls up the fraction bar, which is a really nice feature. If you don't have the fraction bar, be sure to write your entire denominator in parentheses. So t squared minus 24t plus 160. Now, because I do have the fraction bar on my calculator, I don't need these parentheses. It's kind of redundant. But everybody else, make sure you include your parentheses. And then we're going to integrate this with respect to x. Again, I use the variable x, they use the variable t. As long as I'm consistent, that should not be a problem. When I integrate this, I get an answer of 6004.270. 6004.270. Now, obviously, there's no such thing as a fraction of a person, so 6,004 people have entered the park. And then right after 5 p.m., the next person enters. So 5 p.m. Round the answer to the nearest whole number. Okay. This is worth 3 points. The first point comes from having the limits on the integrand. So recognizing from 9 to 17. The second point comes from having the integrand, the fact that you are integrating E of t. And then your third point comes from having the correct answer, 6,004 people. All right, moving on to Part B. Part B says the price of admission is $15 until 5 p.m. And then after that, the price of admission drops to $11, so evening special. How many dollars are collected? Well, this is very similar to Part A. We need to integrate how many people entered from 9 a.m. until 5 p.m. And if we take that and we multiply it by 15, that would give us the total money earned from 9 a.m. to 5 p.m. And then if we add to that the fact that from 5 p.m. onwards, the price drops to $11. So from 5 p.m., which is 1700, until closing time, 2300, this will tell us how many people entered between 5 p.m. and 11 p.m. The cost drops to $11. So cost times numbers plus cost times numbers. Again, we could turn to our calculator for this. Our calculator would return a value of 104,000 0.165. And they say round your answer to the nearest whole number. So $104,048 have been earned. This could probably be broken down into a slightly different approach where you look at these independently and you're like, I earned $15 times 6,004 people, and then to that I earn $11 times this integral being 1,271 people. And if you took that approach, what happens is you get a slightly different rounded answer because there's those fractional persons happening in this, and that value comes to $104,041. So the slightly different approaches yield slightly different answers, and that has to do with the fact that this is a continuous function even though the number of people entering a park is a discrete function. No such thing as half a person. Okay. Regardless, part B is worth only 1 point, and that point comes from having the setup correct. Whether you chose this setup or this setup, it's only 1 point for part B. All right, let's move on to part C. They give us this function, h of t. I'll write it down again, from 9 to t, 9 to t of the entering people minus the leaving people. So what this tells us is the total number of people who have entered subtract the total number of people who have left from time 9 to time unknown t. They tell us that h of 17 is approximately 3,725 people, or sorry, 3,725. And they want us to find h prime of 17. That's what they're asking for. And they also ask us to tell them the meaning of this. So the meaning of this is at 5 p.m., because time 17 is 5 p.m. There are 3,725 people in the park. Because we are calculating the total number that had entered, take away the total number that have left the park. H prime of 17, well, they're asking us to take the derivative of this and evaluate this at 17. So if I take the derivative of an integral, h prime of t, that would be the integrand at the top times the derivative of the top minus integrand of the bottom times the derivative of the bottom. And that cleans out quite nicely to this, so we can now evaluate h prime of 17. H prime of 17 is e of 17 subtract L of 17, which we can rely on our calculator again to evaluate if we wanted to do that. I'm going to save that for the viewer to do off screen, but we plug 17 into the e function, and then we plug 17 into the L function, and we take the difference. $380.281. So if this is the derivative of the h function, and h represents the number of people in the park, this would represent the rate of change of number of people in the park. So at 5 p.m., the number of people in the park is decreasing by approximately, and really that was an approximation, 380.281 people per hour. Does it say anything about rounding? Doesn't say rounding, so because this is a rate function, it is possible to talk about decimals of people. But okay, part C is worth 3 points. The first one is the value of h prime of 17. So if you successfully found h prime of 17, that is 1 point. The other 2 points comes from the meaning. So this meaning, what is h of 17 is worth 1 point, and what is h prime of 17? That's worth 1 point. Now they do have a note here that says subtract a point if there is no reference to time 17. So don't forget to include that these things are referring to at time 17. And I wrote that as 5 p.m., which they've established is t equals 17. All right, moving on to part D. It says, at what time does the model predict that the number of the people in the park is at a maximum? So if h of t represents the number of people in the park, then we need to maximize h of t. Maximize h of t. And we know maximums will occur at endpoints or at critical values, so we need to find when does a critical value exist? When does h prime of t equal 0? In part C, we learned that h prime of t is the same thing as e of t minus L of t. So we're asking the question, when does e of t equal L of t? So the easiest way to do that is, I believe the easiest way is to graph both equations and see where they intersect. So in the top I've done e of t using the old notation with the divide by in the parentheses. In y2 I've done L of t and actually used that numerator bar. And as a reminder, you can find that numerator bar by pressing alpha y equals, and some of the more updated calculators have that n over d, so use that. I want to adjust my viewing window to the appropriate times, so the time is going to be somewhere between time 9 and time 23, because that's when the park is open. And we're looking for, we don't exactly know what our y min and our y max values are, so I'm just going to say at a minimum we have 0 people in the park, and at a maximum, I don't know, we'll go with 3,000 people in the park. I probably could give some more thought to that, but let's see if that works. So there's the number of people entering the park, and this is the number of people leaving the park. And so right there is the intersection where the number of entrants is equal to the number of those left. And that's what we want to find out. So by pressing second trace, we can pull up the intersect command, oops, which is option 5. And the intersection is, fortunately my cursor is really close to this, so I can just hit enter 3 times. They intersect at t is approximately 15.794. Or in AP grading, they accept rounded or truncated, so 15.795 is another approach. Okay, this is worth 2 points. 1, if you were to establish the fact that this needs to be true, the function is going to be maximized at the critical values. And then 2, if you have the correct time. Now technically I should run the candidates test on this because we're looking for an absolute maximum. but logic tells me there's no people in the park when it opens at 9, so that is going to be smaller. It'll be 0, the number of people in the park, as well as when the park closes at time 23, the number of people in the park will also be 0 or close to 0. So there we go. That's the maximum. If we wanted to do a different analysis, we could look at the fact that h prime goes from positive to negative. Therefore, h goes from increasing to decreasing at that time. That's another way to show that that is a maximum. All right, thanks for watching. Ask good questions, conquer the world.